In two-dimensional motion, we'll be looking at displacement, velocity, and acceleration in two dimensions. What is two-dimensional motion? We think of a cube as having 3 dimensions because it has a length, a width, and a height. Each of these, length, width, and height, is a dimension. A one-dimensional space, then, would just include one of these, say length. With just length, you have a straight line. So if an object is moving in one dimension, it's moving in a straight line, and we often call this linear motion. In two-dimensional motion, an object can move along 2 dimensions, say the length and the width of the cube. These 2 dimensions make up a surface, like the top or the bottom of the cube, for example. An object moving in 2 dimensions can move anywhere along this surface. We often visualize 2 dimensions with an xy graph, where x is the horizontal axis and y is the vertical axis. An object moving in 2 dimensions moves a certain amount in the x direction and a certain amount in the y direction. An example of two-dimensional motion is a car moving along a curved path on a plane. We will first look at the displacement of the car on the path. Remember that in one-dimensional motion, the displacement of an object is the difference between its final and its initial positions. So, if at time t0 our car is at this location, vector d0, from the origin, and at a later time t, our car is at this location d from the origin, then the displacement of the car is the new vector delta d, which equals d minus d0. Two-dimensional displacement is also the difference between the final and initial positions of an object. Let's say the initial location of our car on the path is here. We need to draw an origin in order to have a vector that gives the initial location of the car. So we draw our xy plot. The initial position of our car can now be given by this vector r0. Later, at time t, our car is at this position, which we give by the vector r. The displacement of our car is now given by this vector, delta r, which shows the change in its position from time t0 to time t. Just as in one-dimensional displacement, delta r is the difference between the vectors r and r0. If you recall, average velocity is equal to the displacement of an object divided by a given time interval. So in this case, average velocity equals delta r over delta t, which equals r minus r0 divided by t minus t0. The average velocity vector has the same direction as the displacement vector. Average velocity gives us the average of the car's velocity from time t0 to time t. Instantaneous velocity is the velocity of the car at any instant. If this curve marks the path that the car traveled, and we found the velocity of the car at a time t1 when it was right here, the instantaneous velocity vector would be in a direction tangent to the path of the car at that point. A line that's tangent to a curve touches the curve but does not cross it. Finally, average acceleration, just as in one-dimensional motion, is the change in the velocity over time. This is the direction of the average acceleration vector, therefore is in the same direction as the change in the instantaneous velocity. So displacement, average velocity, and average acceleration have the same basic definitions in two-dimensional motion as they do in one-dimensional motion.